I will be presenting cybersecurity intrusion detection system using machine learning. So this project focuses on building a predictive model that can detect whether a network session is normal or an attack based on different network features. So we use Python and several machine learning models to analyze a dataset of network traffic and classify whether an intrusion is happening or not. The dataset we use is a cybersecurity intrusion detection dataset combining around 9,500 network session records. Each row represents a session in a network, and session has multiple features like packet size, protocol type, login attempts, session duration, browser type, and IP reputation score. The main input features include network packet size, protocol type, TCP, UDP, or ISMP, login attempts, session duration, failed logins, browser type, IP reputation score, or and unusual time access. So these features represent user behavior and network activity, which are important indicators of cyber attacks. The target variable is called attack or detected, which is a binary value, which means zero is normal activity and one means an attack or intrusion. For data cleaning, the first step use is we remove unnecessary columns, and the session ID column was dropped because it is just an identifier and does not contribute to predicting whether an attack happened or not. Also, the encryption use column to reduce to categorical complexity and simplify the dataset. After that, dataset to check the by its quality by looking for missing values using is null and checking for duplicate records using duplicate. So in this dataset, there were either no missing values or only minimal ones, and also confirmed that duplicate records were properly handled. This step is important because cleaning the dataset improves model performance and removes unnecessary noise that could affect prediction accuracy. In this step, we applied label encoding to convert categorical variables into numerical form. This is necessary because machine learning models cannot directly understand text like TCP, UDP, or browser names such as Chrome and Firefox. So we use label encoder to transform these categories into numbers. So for example, protocol types like TCP, UDP, and ICMP were converted into numeric value like 0, 1, and 2. Similarly, browser types such as Chrome, Firefox, and Edge were also converted into numbers. This step is important because it allows the machine learning model to process data properly and include these features in training and prediction. In this part, we use standard scaler to normalize our dataset. So the purpose of standard scaler is to transform all features so that they have a mean of 0 and a standard deviation of 1. This is important because in our dataset, some features like session duration and packet size have very large values compared to other like login attempts. So if we don't scale the data, the larger values may dominate the model and affect the prediction accuracy. So by applying scaling, we ensure that all features contribute equally to the model. So this also helps machine learning algorithms converge faster and perform better, especially models like regression that rely on distance and gradient-based optimization. In this step, we split our dataset into training and testing sets using the train test split method. So we use 75% of the data for training the model and 25% for testing it. The training set is used by the model to learn patterns from the data, while the testing set is used to evaluate how well the model performs on unseen data. So this step is very important because it ensures that the model is not just memorizing the data, but actually learning patterns that it can generalize to new inputs. So if we don't separate training and testing data properly, the model might overfit and perform poorly in real-world situations. So we also use a random state value to ensure that the results are reproducible every time we run the code. In this part, we tested multiple machine learning models to classify whether a network session is attack or normal. We use different models including random forest, decision tree, other boost, logistic regression, gradient boosting, and naive Bayes. The reason we use multiple models is to compare their performance and identify which one works best for intrusion detection. This also helps us understand the difference between linear and nonlinear models. So, for example, logistic regression is a linear model, while random forest and gradient boosting are nonlinear models that can capture more complex patterns in the data. So, by comparing all these models, we can determine which algorithm is most effective for cybersecurity intrusion detection systems. This dataset is important because it simulates real-world network traffic and includes both normal and malicious activities. It represents user behavior like network activity and security-related indicators such as failed logins and IP reputation. In cybersecurity, this type of dataset is useful for training intrusion detection systems that can automatically detect attacks. It helps identify threats early and reduce the need for manual monitoring, making cybersecurity system more efficient and intelligent. In this part, we explain how the machine learning model works step by step. So first, input features are collected from the network datasets such as login attempts, packet size, and session duration. So next is data goes through preprocessing, including encoding and scaling, so the model can process it properly. After that, the model learns patterns from the training data and builds either decision rules or weighted relationship depending on the algorithm. Then we pass the test data into the trained model. So finally, the model outputs a prediction where 0 means normal activity and 1 means an attack. This shows how raw network data is transformed into a final cybersecurity decision. In this section, we show the data processing pipeline for the system. It starts with raw network data, which contains both numerical and categorical features. Next is categorical values are encoded into numbers so that the model can understand them. After that, feature scaling is applied to normalize all values into a consistent range. Then, the model is trained using this processed data to learn patterns of normal and attack behavior. And finally, the model generates predictions, either normal or attack. The key idea here is that data is not used directly, so it goes through multiple transportation steps to improve accuracy and make the model more effective. We relate the machine learning model to linear systems theory. So the model can be seen as a system where the input is the network picture vector, and the output is a prediction, either normal or attack. So we can represent this as a function where the model maps input data to output decisions. So the system behavior is learned from historical data, meaning it improves its understanding based on past examples or normal and malicious activity. So before reaching the model, the data goes through transformations like encoding and scaling, which prepare the raw data into usable form. In linear systems theory, the model can also be compared to signal processing system. Network data is treated like signals, and preprocessing helps remove noise and extract useful information. So the model's stability refers to its ability to produce consistent results even when small change occur in the input data. Ensemble models like random forest improve stability by combining multiple learners. So finally, the feature mapping is how the model transforms input features into a decision output, where it learns relationships between variables and produce a final prediction of attack or normal behavior. So even though some models are linear, most of the system is actually nonlinear due to complex decision boundaries. In this section, we compare linear and nonlinear behavior of the models used in our system. So logistic regression is considered a linear system because it is uses a weighted sum of input features to make predictions. So this means it creates a linear decision boundary based on the combination of input variables. On the other hand, tree-based models like random forest and gradient boosting are nonlinear systems. So deci- they use decision rules and branching logic instead of a simple mathematical equations. So these models are able to capture more complex patterns in the data, especially in cybersecurity scenarios. Because of the models we use are tree-based and ensemble methods, the overall system is considered mostly nonlinear. In the program execution process. So we first load the dataset into the system, then we remove unnecessary columns such as session ID and encryption type. After that, we separate the input features and the target variables, which is attack detected. So finally, we split the dataset into training and testing sets so that the models can learn and later be evaluated. In the training and testing phase, we did not only use one model. So we trained multiple models such as random forest, decision tree, other boost, logistic regression, gradient boosting, and naive Bayes. Each model is trained using the same training dataset after applying feature scaling. Then each model is tested using unseen data to generate predictions. So this allows us to compare different algorithms and determine which one patterns best for intrusion detection. So here, we analyze the performance of all machine learning models used in the system. So from the results, we can see that random forest achieved the highest accuracy of around 89.56%, make it one of the best performing models. However, the gradient boosting also performed very strongly with 89.40% accuracy and a very high precision of 100%. Adobus also achieved perfect precision, but its recall was slower, meaning it missed some actual attacks. Precision 3 and iBase performed moderately, while logistic regression had the lowest performance because it is a linear model and cannot fully capture complex patterns in cybersecurity data. So overall, we can conclude that ensemble models like random forest and gradient boosting perform better because they handle nonlinear relationships in the dataset more effectively. There's also a trade-off between precision and recall, which is very important in cybersecurity. Like high precision means fewer false alarms, while high recall means better attack detection. So depending on the use case, we may prefer gradient boosting as the most balanced model. In this slide, we test the model using a sample input that represents a network session. The input contains values such as packet size, login attempts, session duration, and IP reputation score. We pass this input into the trained model to get a prediction. Then the output will either be 0, meaning normal activity, or 1, meaning an attack. This helps us to test how the model behaves with real world like data and validates its prediction capability. The most important thing I learned is the full machine learning workflow. So I understand how raw data is processed step by step until it becomes a trained model that can make predictions. Also learn how classification models are used in cybersecurity to detect whether network activity is normal or malicious. So overall, I realized how important features are in helping the model understand attack patterns. This activity also helped me understand how machine learning is applied in cybersecurity. It is very useful in automatically detecting attacks and identifying patterns that are not easily visible to humans. So, predictive models are important because they allow early detection of threats before they cause damage. They also reduce the need for constant manual monitoring and help improve real time security systems. This activity also helped me relate machine learning to linear system theory. The model behaves like a system where input features are transformed into outputs through a defined process. This is similar to signal processing, where raw data is transformed into meaningful output. Therefore, I encountered challenges such as encoding categorical variables and comparing multiple models, but I was able to solve them using preprocessing and evaluation techniques. So that's all. Thank you.